multiple reasons. The first reason why I wanted YouTube was that depending on the bandwidth available to you, you could watch the video on a desired resolution. Okay, so you'll not be limited by the resolution with which I can upload it on Google Drive or something like that. These videos are mostly made in 720p. So 720p downwards, you can have various resolutions, whatever your bandwidth supports. So hopefully that will be helpful. And also it will just stay, it's a private shared video. So hopefully it will stay there for you to come back and listen to it if it's of any help. So we'll start with today's class, and if you remember correctly, what we were doing in the last class, we took a look back at Newton's laws, and what I was trying to portray to you is that the mere statement of the three laws assumes a lot of stuff. A lot of stuff is said between the lines in stating the Newton's three laws. And I was also trying to show you that in case those assumptions broke down, be it that you were in a non-inertial frame, be it that that action is not always equal to reaction, such strange things do happen in life. And I was trying to give you examples of two charged particles. I think that's where I ended my discussion the last day, which is there on screen now. In all such cases, we will see that these are misinterpretations or inadequate interpretations of Newton's laws. You might accuse me that in all such circumstances, I am desperate to save Newton's laws. But nevertheless, even if you make that accusation, nevertheless, it goes to show that how far can the scope of Newton's laws be expanded? So let's come back to the problem of the two charged particles. So the problem was that you have two charged particles, 1 and 2, with charge Q1 and Q2. It doesn't really matter. Two charges Q1 and Q2 moving with velocity V1 and V2 along the x direction and the negative y direction. And the question you were asked was, can you actually write down the force experienced by these two charged particles due to each other, the interaction force? Okay. Can you write those down? And is action really equal and opposite to reaction? Can we actually see that? And we went on to write the force on the first particle, F1, due to the second particle. That's why we have the subscript F12 will be equal to Q1 V1 cross V2, where V1 is the velocity of the first particle and V2 is the magnetic field due to the second particle at the position of the first particle. And similarly, we could write an expression F21 for the force experienced by the second particle due to the magnetic field of the first particle. And if you look at this Lorentz force term, we easily realize that you see these forces are not equal and opposite to each other. And I left it as a homework to you to figure out what are the values of the two forces, and hopefully you have done that. So in this case, we see that apparently Newton's third law is being violated. That the one force is not equal and opposite to the other force. Let's take a more critical look about how this thing is going to affect us. And you can say, so what goes wrong? You will see what goes wrong. So what I'll do is, I'll again begin with a very the simple definition. So you see what I wrote in the previous page. I started off saying that, look, this is P is the total momentum of the system of particles. And this total momentum of the system of particles is obviously given by the sum of the individual momenta. That is the principle of superposition that I have been speaking about. And this is nothing but equal to summation over I m vi, where m is the inertial mass, which can also be written as m r1 dot. Right. So this is our expression for mechanical momentum. This is our expression for momentum. And Newton's law basically tells us that the rate of change of momentum should be equal to. So if you notice carefully, I have taken the total momentum of the system of particles. So the system of particles can have n number of particles. I don't know how many is n, but I'm looking at the total momentum. And the rate of change of the total momentum is equal to, sorry, I made a mistake, is equal to the force applied. Not the rate of change of force applied, but the force applied. The external force applied. Okay, now this also means, this also implies that in case F external is equal to 0, this is also equal to 0, and which would imply that the total momentum is a constant or is a conserved quantity. And this is how we interpret this kind of, intuitively matches our understanding of Newton's laws. What about the angular momentum?
Sir, your mic is off.
Yeah, hopefully I am back. Something went wrong with my iPad. I don't know what. It suddenly said it has stopped broadcasting. So hopefully you can see my screen again and you can hear my voice. Okay, what about angular momentum? So for the same system of particles, if I try to write down the angular momentum, then I would have essentially written it like so. Okay, exactly following what I did earlier for the linear momentum part, and that would be again the summation of Ri cross Pi. Okay, what about the rate of change of angular momentum? The rate of change of angular momentum would have been written as these two terms. Okay, let's look at the second term. Okay, let's look at the second term after the summation sign. So that's summation of Ri cross Pi and Pi dot. So what is Pi dot? Pi dot by our previous definition would have been the force acting on these individual particles. So the force acting on any individual particle would be essentially given as a sum of two quantities, Fij. Uh, Again, it would be a summation of Fij due to the jth particle, force on the ith particle due to the jth particle. That's the interaction force, plus any external force which is acting on the system. Now, if I assume for the time being that they know the external force acting on the system is 0, then this term kind of cancels off. And this term And this term, is what is left. Maybe I will, for the time being, I will not assume that the external force is zero. So I'll just keep both the terms here, just to show you what happens. So I'll just go on with that. Ri cross F. Okay, I just can continue with that term. Now, if Newton's third law is valid, and kind of, Fi is equal Fij, between any two particles, pair of particles, is equal and opposite to each other, then look at this first term. Okay, if there are only two particles and the force of interaction is linear between the two, you can pretty well understand that that if this will again turn out to be zero. And what will be left out with this is the last term. And if the last term, if the force external is also zero, then what we get is that dl dt will essentially be zero. And a similar thing can be argued for the first term also, if you actually break it up, where you have ri dot cross pi, which is nothing but summation of mi ri, and you can made a mistake. It's basically mi ri, and you can work out the same, and you come to the same conclusion. And
So it would be MIRI dot.
No, it's momentum, right? Sorry, yeah, sorry, yeah, that's true, yeah, that's true. Yes. So I will actually have a similar term here, and I would leave it to you to do the calculation for this. That what do you get as you continue with this calculation? So the main thing which comes out of it is that if the external force is zero, and you have a force field which is along the vector connecting the two particles, and Newton's third law is valid, we'll end up with a situation that dl dt is going to be conserved if the external torque on the system is actually zero. That is what we conclude from this whole exercise. So if I apply this understanding back to those system of two charged particles there on the screen, what do we get? I would ask you all to work out that what do we get if we had purely electrostatic interactions, where the interaction force, or Fij, between the two charged particles will follow Coulomb's law in the first instance, and they will be directed along the vector joining each other, and then say, well, no, let's neglect the Coulombic interaction, and let's look at the electrodynamic interaction, which follows the Lorentz law. What happens then? There is no external force acting on the system of particles. You have just two particles, and they are moving under mutual interaction with each other. So if they are repelled, they are repelled. If they are attracted, they are attracted. You can assume your own initial conditions just to set up the problem, that you can imagine, or you can assume that at time t is equal to 0, the first particle, there are two charged particles. The first particle is at a point P1. The second particle is at a point P2. And both are the same charge, okay, QQ, let's say, for the sake of simplicity. And at time t is equal to 0, they are let loose. Okay, they are let loose, or and they actually fly away from each other due to repulsion. Or you can assume that at time t is equal to 0, it so happens that this charge was moving with a velocity, uniform velocity, like so, and this charge was moving with a uniform velocity like so, and that's when I start observing the two particles and look at the forces of interaction. Write the forces of interaction, assuming purely Coulombic interaction, Write the forces of interaction, assuming the Lorentz force is present and cannot be neglected. And then still assuming that F external acting on the system is 0, just try to see, are the linear momenta, the angular momenta of this system, of mutually interacting system, conserved? Are the torques 0? What happens to them? And you will see that our definition of momentum, the way we have defined momentum, will be called into question. But I think all of you, I would advise all of you to necessarily go through this exercise, okay, so that you understand where the problem lies. Okay, so and obviously I'm bringing all this up because just to show you that the principle of conservation of linear momentum on angular momentum will be violated. Okay, does that mean it is really violated, or there is something wrong with our understanding or the way we have defined the momentum of the system? And I'm sure most of you also know the answer, that the correction term essentially comes in terms of the field momentum of the system, that the electromagnetic field itself carries momentum, and that is to be accounted for if you actually want to preserve Newton's law, or you want to interpret Newton's law correctly in this given system. Okay, so therefore you see what I am again trying to kind of portray to you is that the way we have been taught Newton's laws, the way we have been asked not only to conceptually understand Newton's laws, but mathematically formulate them, there is something missing. That you have to constantly go on updating my definitions of momenta, my definition of what is exactly force to begin with. So therefore, that is again a limitation or shortcoming of the mathematical formulation, the analytical formulation of Newton's law as we have been taught. And that is partly what classical mechanics or analytical mechanics, the Lagrangian formulation, the Hamiltonian formulation, hopes to correct. That it actually gives you a prescription. It gives you a prescription where it does not depend from system to system, whether it's a particle, whether it is a field, but the prescription is general enough to actually handle all of these situations. So let's see how we go about doing this. Okay. So again, it's a bit of all this is a bit of a recap, trying to point out the problems to you. So so if I am given a mechanical system, because I'm speaking of mechanical systems because that's what you are mostly used to. If I am given a mechanical system and I ask you to describe the motion of the mechanical system, it can be a pendulum, it can be a spring and a bob, it can be a particle moving down an incline, etc., etc. It can be really anything. But central to this description of motion is the concept of that point particle. Okay, so first thing we'll have to do, which we intuitively do, is that we categorize that is a point particle description good enough, or is an extended extended system description actually needed. And again, the answer is very simple. For example, if you want to describe the motion of the pendulum swinging back and forth, or even the earth going around the sun, you would say that a point particle description is actually fine. But if you want to describe the rotation of the earth or the spinning nature of the top, then you would find a point particle description inadequate. Hopefully you understand the difference. In the second examples, you will definitely have to build into your analytical description the physical extent of the object. So you can't have a point top and make it spin. Neither can you actually have a rotating earth, which is a point particle. Okay. So therefore, depending on what am I supposed to describe, the idea of a particle changes. The idea of a particle changes. And what our observations has shown, physical observations, kinematics has shown that if we actually describe or define the position and the velocity of a particle at all points of time over which I want to know its motion, then the system is fully defined. So then what does the Newton's law actually tell us? What does Newton's law actually give us? Okay, so what I'm saying is that, you see, you have to specify the kinematic variables. Okay, you have to specify the kinematic variables, which are position and velocity of a point particle, let's say. I'm not going into an extended system at this moment, or an extended rigid body at this point, simply because we'll have to define additional coordinates for them. But as of now, let's stick to a point particle and let's stick to its kinematic variables, which are given by position and velocity. Given Newton's laws, it actually gives me a relationship between these quantities, a causal relationship between these quantities, and helps us compute then that motion, that deterministic motion over the entire time interval that we have actually specified. Now, when talking about these two quantities called position and momentum, okay, we like to call them degrees of freedom. Okay, but in saying that, these are the degrees of freedom of a particle, again, just like the initial statement of Newton's laws, I have left a lot of things unsaid, and that's something which we will try to figure out, that what have I left unsaid. So if a particle is at rest, okay, how many coordinates do you need to specify its position? So in a three-dimensional space, you will need 3 coordinates. Okay, so I will just write that down. Okay, I will just write that down. I'll add a page. So I'll add a page. So I have, so let's say, okay. Degrees of freedom. So now, so in a three-dimensional space, I have 3 coordinates. Three coordinates are necessary, which are essentially nothing but the position, the x, y, z. Okay, or if you are in a different coordinate system, you can think of r, theta, phi, or you can think of rho, phi, z, etc., etc. So irrespective of which coordinate system you actually are using, you will require 3 position vectors, okay, or 3 position coordinates, sorry, not vectors, 3 position coordinates to uniquely describe the position of this particle. And if there are n number of such particles in the system, okay, so per particle it will essentially be 3. So you will have 3n number of position coordinates to define. Now, the mere statement again presupposes the existence of at least a reference frame, which is nothing but the coordinate system. So I know where my 0, 0, 0 of the frame is, with respect to which I will define these positions there. Okay, these positions there, and so on. Okay. So as I have told you that the right reference frame has been defined is given by Newton's first law, that it's a reference frame where the Newton's laws are actually valid or can be verified, is the right reference frame. The right reference frame in which you can actually work. So what do we actually say further about it? So once we have defined the position vector, I would like to know ideally what is this position vector as a function of time. So so I have the position vector, and I would like to know what is this as a function of time. This is finally what I want to know, which is the trajectory of the particle. But this is not something which I have a priori. This is not something which I have a priori. But if you remember from your school days, you have seen statements like this, where U and A are constants. Okay, I am sure you kind of recognize this statement, or you have seen statements like A. This is what we finally want to arrive at. This is what we finally want to arrive at. And needless to say that the first is a solution of a particle moving with an initial velocity u and uniform constant acceleration a. Okay. And what is the position of the particle as a function of time? With two parameters in the system. One is the initial velocity, the other parameter is the acceleration, both of which are constants. The second equation obviously shows you an oscillatory motion where the parameter A is the amplitude, omega is the frequency, and phi is the phase of the system. And these are the kind of equations that we actually want to derive by solving Newton's law. So the first one essentially gives you rectilinear motion. And the second one actually gives you simple harmonic motion, or SHM, an oscillatory motion. This understanding obviously can be extended to multi-particle system, and as I told you that Newton's second law, the second law of Newton's second law essentially becomes that the sum of the rate of change of momentum of a system of particles is essentially equal to all the interactions that are actually taking place. So let's maybe I'll just write it from for a single particle system and then kind of move up. So I can easily write that Pi is equal to the sum of the external forces acting on the ith particle. So these are the external forces plus Fij, again sum over j. Okay, sum over j, and these are the forces acting on the particles. Now Newton's third law, if we actually assume Newton's third law to mean, if we assume, so therefore be very careful what I am writing. If the third law is assumed to say that is equal to Fji, and if we sum over all particles, now if we take a sum over all particles, then what will we get? If we sum over all particles, we will essentially get something like this, that dt square sum over mi. So you see, this is another way of exactly what I was trying to tell you in the previous slide, that if Newton's third...
There should be minus sign.
Come again?
There should be a minus sign in the third law.
Sorry, this one, right? This is what you meant. Sorry, I was writing.
Yes, sir.
Sorry, this is
Yes,
what.
sir.
Yeah, I was just writing the magnitude though, because the direction will be opposite. Yeah, but if that's what you mean, yes. So the thing is that you have Newton's third law, and if this is how you interpret it, then it is all fine. But you saw via the previous example that the moment this thing doesn't happen, then the definitions from the beginning is actually called into question. Okay, let's move to a much more simpler thing of the degrees of freedom and coordinates. Let's look at a simple pendulum. Okay, so let's look at a simple pendulum, and in a simple pendulum you have a bob. A simple pendulum, you have a bob, and so that's the vertical, and you have a string there, and that's the point particle. Okay, that's the bob, the pendulum bob, and I'll assume that it is a xy coordinate system, a Cartesian coordinate system, and obviously the center of mass of the bob actually has a coordinate, the coordinates xy. Okay, and okay, I'll come to the theta later. Okay, let's forget it for the time being. Okay, you have the vertical, and there you have. There you go. So if you specify the x and the y coordinates of the system, and in principle, if you solve Newton's law, if you actually figure out x as a function of t and y as a function of t, then you have actually solved the problem. You have actually solved the problem. But you see, there are the problem is more complicated, or can more complicated than it actually looks, and in some sense it can be further simplified. How can it be simplified? It can be simplified because these two coordinates x and y are actually not independent coordinates. They are not really independent coordinates, but they are there is a relationship between them via the string. Now the string has a length L. The string has a length L, and the string not only has a length L, it also is taut. That means it doesn't slack. So which means that all throughout there was a constraint in the system which basically said so from a free particle point of view, it basically is telling us that the distance of this bob from the point of support or origin O, which was the 0, 0 of the coordinate system, the bob moves in a fashion such that this condition is always satisfied. Now, in the in a plane polar coordinate system, so this is what I wrote in a Cartesian coordinate system. If I wrote the same equations in a plane polar coordinate system, my coordinates would essentially be r and theta. My coordinates would be r and theta, and in principle, I would ask you to solve for r as a function of t and theta as a function of t. And if we do this, make the solution, you know that we'll have the answer. But that is a problem, because what this constraint is actually telling us is that r is a constant. So the radial distance from the origin of the system is a constant. So that doesn't change as a function of time. And this is given at the when you actually state the problem. We probably do it intuitively. You must have done it intuitively. But this is something which is stated when you actually conceptualize the problem, that describe the motion of a particle under the action of gravitational field. Like, so the pendulum will be under the action of the gravitational field pointing downwards, subject to the constraint that the distance of the particle from the origin is a constant of time. And that is really the statement of this of the what we say, that the string is a massless rigid body. So we neglect the mass of the string. The string is massless. We also assume the string is always straight and taut. It never slacks. And all of that is essentially mathematically stated in this one simple constraint equation: r is equal to constant, or x square plus y square is equal to L square, and L is a constant. Let's look at another example. So let's look at an example where I have the floor. Okay, I have a floor which is at z is equal to 0. Okay, I have a floor which is z is equal to 0, and you can just imagine that that's my coordinate system, x, y, z. Okay, that's my coordinate system, and what I do is, at some arbitrary height h above the plane, or this whatever I am calling the floor, I take a ball and I drop it down from rest. So initially it's at t is equal to 0, 0, z was equal to h. Okay, that is the height from which I drop the ball, and I just drop it. Now what is going to happen? What is going to happen is that you know pretty well what is going to happen. This was it had a potential energy mgh. By the time it actually comes here, that potential energy will be lost, and will be turned into kinetic energy. Okay, and depending on the coefficient of restitution, and if I just assume it to be perfect, that no energy is lost in the collision. It's just that the velocity is reversed. Then with the same kinetic energy, the ball will bounce upwards back, reach the height, and go on doing that. Now, in describing the motion of this particle, this point particle, is there an equation of constraint? There is actually an equation of constraint. So can anybody tell me what is the equation of constraint, or you can actually write it on the chat box?
The ball will never go below 0.
That's right, Shamrat. The ball will never go below 0. So what is the equation of the constraint?
Z greater than or equal to 0.
That's right. So the constraint, the equation of the constraint is that z is more than equal to 0. And I've obviously taken the ground as 0. If you could have taken the ground as anything, z is equal to a, and then the equation of constraint would have changed to z is more than equal to a. It doesn't really matter. So in the first example, I saw that there is something called constraints came into picture. Okay, and constraints, the first constraint was equality. R is equal to 0, R is equal to a, some constant, or x square plus y square is equal to a square was a constant. That was the case 1. The case 2 is a constraint which came in the form of an inequality. Okay, in the case of an inequality, there was an equal, but that was a special case, that z was always more than equal to 0. You have actually phrased another constraint before. In the first 2 classes that we actually discussed, you have seen another constraint, and that constraint was the rigid body constraint. Now, in defining a rigid body, if you remember, I had given you a constraint something like this. So this was also another constraint which was brought in defining a rigid body, that the distance, a body is composed of point particles. However, the distance between the point particles are fixed, are constant. Between any 2 pair of point particles is a constant. So that was again another constraint which was actually associated with the definition of the rigid body. So you can, there are thousands of examples. I can just, go on. So if I have a box of gas, and what I do is that, the side of the box is a square box. Okay, then I can say that, the constraint on the on the particle is the constraint on the particle is this, or I mean on all the particles. So these are the equations of constraints. But if you look at it, each of these equations of constraint actually does something very strange. The first example I took, the pendulum. In that very specific example, the equation of the constraint or the presence of the constraint itself actually gave rise to a force acting on the system. Can anyone tell me what was that force acting on the system? Which arose simply because the constraint was actually there.
Tension.
Tension.
Yeah, you are right. It is the force of tension. And which, when we drew the free body diagram, we had to bring it in. We had to bring it in and say, well, there must be tension. Otherwise, we can't explain the equations of motion of the system. So if you wanted to write F is equal to ma, I had to bring in that tension. It's only after I incorporated tension that I could actually completely write Newton's equation of motion and actually go ahead and solve it. Hopefully, all of you have actually solved the equations of motion for a simple pendulum. If there is anyone who hasn't started from scratch and gone ahead to solve the equation of motion, trying to derive the time period, trying to derive the x as a function of t, y as a function of t, etc., etc., my honest request to all of you would be, please go ahead and do it. Just do it once. Do it once in the Cartesian coordinate system and do it another in the plane polar coordinate system. But do it. When I actually spoke of z is more than equal to 0, was there a force of constraint? Anyone?
Yes, sir, there is a force, but for very small time period, there will be a force when the ball hits the particle, like Dirac delta function type
So what
force.
about the gases in the box? That force of constraint gives you something very physical.
Suppressor.
Yes, it gives you pressure. So the collision of these particles with the walls of the system, which I have described as a force of constraint because the box is constraining the system of particles within a fixed volume, extracts its pleasure in the form of pressure, if you know what I mean. So the box says that you particles cannot move out from this space. You are restricted to within this space. And the way the particles react to this demand is by exerting pressure. So this is the necessary necessary completeness which is derived from the system, that there will be pressure on the walls, and it's a absolutely physically measurable, realizable quantity, just like tension. So if somebody asked you to prove what is the physical reality of that tension force, the force of tension, you are saying that there is an extra force which has come into the picture, and that is tension. Can you actually measure that tension? So think about it. Can you actually measure tension? So I'm sure you know how to measure pressure, the pressure exerted by that box of gas. But how does one measure tension? What is the experimental apparatus which will allow you to measure tension and then actually quantify and say, well, that is the tension that we have been speaking about? Okay.
So I think Melde's experiment.
Yeah, I've forgotten Meldy's experiment. What does that experiment do?
There is a string. It uses the standing wave standing
Yeah,
wave U.
yeah,
And
but in the concept of a pendulum, how do you set up a standing wave equation?
oh, right there you.
So you need to do something much more simpler, isn't it?
You can only know the tension after solving the problem.
No. Look at the formula of Newton's law. You see, how did I formulate it? I said that you know the coordinates of a particle. You know that if you specify, the basic assumption is if you specify the position and the velocity of the particle, this is kind of mechanical point particles, huh? This,
Okay.
it will satisfy, it will allow you to calculate r double dot, Okay, and if you put it in Newton's law, it will, the either side, the left hand side will be equal to the right hand side, isn't it?
Yes.
And there you see what was there on the right hand side. On one side it was, you know, mr double dot, or the rate of change of momentum. On the other side you had force. So you can't come back and tell me I will measure force as a result of my calculation.
Yeah. It will be like circular logic.
Yes, yes, yes. So an accelerated frame did not work before, because I could not ascribe the forces to its origin or causal relationship. So I can't go on in a chicken and egg problem. Okay, so I have to independently in an inertial frame, should be in principle though. I'm not saying that you actually have to do it, because the other selling point of Newton's law is that, you know, I can the principle of superposition is valid, blah blah blah. All of that is true, but in principle, I actually can measure each of these forces, each of the particles' position, each of the particles' velocity for all times of interest, isn't it? Only then can I actually go down and prove the validity of Newton's laws. So therefore, the simplest question is, how do I measure force? So if I told you that, you know, the gravitational force, the acceleration due to gravity acting on the pendulum mg, how do you prove it? I'm sure you can do a you can do an experiment to prove it. What about the tension? Is there a physical reality of tension? So just think about it. That could you have measured, that calculated value of tension? Could you have actually measured it? And if so, how? Okay. So let's come back to the constraint. So you see, therefore, what I have essentially showed you, is that that constraints can be broadly classified into two forms. Okay, so the algebraic equation describing the constraint can be classified into two forms. One is an equality, the other is an inequality. Okay, so the first class of problems essentially tells you that the constraint can be expressed with an algebraic equation of the form f as a function of r1, r2, r3, r4, essentially rn, how many number of coordinates there are applicable to the system. Okay, and this is equal to 0 is such an equation can actually be written. Okay, the other tells you that, well, you can write that equation in terms of the Ri, but you can only write a inequality. Okay, you can only write a inequality. And if this happens, so these are the two general class of constraints. We will complicate it further, but for now, these are two general class of constraints that we actually we work with. And the first constraint, first class of constraints are known as the holonomic constraints. And the second class of constraints are known as non-holonomic constraints. Okay. Okay, maybe, yeah, I'll take a break now. Okay, so Siddharth is trying to answer something. Okay, I missed it. Manas says, sir, can we do it by measuring the elongation of the string in situ? We know the Young's modulus, so we can find out the stress and the hence. It's a massless rigid body, the string. Okay, so.
Excuse me, sir.
Yeah, go ahead.
Sir, I don't know if it's correct to think in that line, but when we have a pulley system, if we have a pulley system, obviously the tension will only exist if there is some weight pulling it down. So there's gravity. It's due to the virtue of gravity. So where there we can, like, usually where we form the equations of motions, from there we measure tension. What's wrong with that?
There's nothing wrong with that, but how will you get the value of the tension? So you will have to, for example, okay, let's start with a very simple system. We start with a simple system saying that, you see, that a block is resting on a surface. Okay.
Okay.
Yeah. And if the block is just resting on a surface and action has an equal and opposite reaction, that helps us define the normal reaction on the system, isn't it?
Right.
Assuming Newton's third law.
Okay.
Right? That's a mechanical system. Third law is valid in its present form. Okay, it's not like those pair of charges, right? So everything is fine. and I calculate the normal reaction, and there I'm absolutely fine. But now think of the bob. Okay. Now, when you think of the bob, if the bob is hanging, okay, vertically downwards, then the bob is at rest. It's in equilibrium, right? It's a static equilibrium. And once we are in static equilibrium, the force acting downwards is mg, and there has to be a tension acting upwards. Something has to balance that. Otherwise, the bob would have fallen down. Right? So therefore, our application of Newton's law would essentially tell me that the entire external force acting on that point particle, namely the bob, is zero. Isn't it? And the moment we make that assumption that it will be zero, because it is not moving, okay, because it is not moving, immediately it will allow me to make a deduction that the tension must be equal and opposite to the force.
Right.
Okay, and the point is taken. Okay. Right. But now I actually ask you that the bob is moving. Right? The bob is moving, and the force, and is tension a constant along the entire motion? No.
No.
So then the question arises that how am I supposed to measure it? Will it be equal to mg at all points of time?
No, sir. No.
Sir, I think you said that we have in classical mechanics, its trajectory is defined. We can, in principle, know its velocity and its position at all points in acceleration.
Because the position r of t is basically my holy grail, right? I want to calculate the trajectory of the particle. What I know is, in principle, if I specify all of this, my problem is solved.
So, like to measure the tension, we can like calculate velocity. We can, in principle, at least calculate.
Yeah, I know. I mean, you see, I'm an experimentalist. Okay, so I don't want to calculate things.
No, I mean, sorry, I meant measure the velocity. I meant measure the velocity at
But
points.
I will not be measuring force. I want to measure force.
What's it? It will mv square by r equal to g cos theta minus t, t minus g cos theta. Can then you and we
Deviation at all points.
Yes. Yes.
Sir, I would suggest using a traveling microscope. So what we can do is first, when the bob is hanging straight, we can just measure the length, and then when it goes to a particular theta, there we use a traveling microscope to just look at the coordinates. And what we can do hence is we know the Young's modulus, and we also know that in that way I think we can plot tension as a function of theta.
What happens if I do this? Let's say I take a small spring balance. Okay. I take a small spring balance and use that as my support. When I hang the string from the spring balance, it will actually give me the weight. It will actually give me the weight of the bob, isn't it?
Yes.
Now what I do is I actually let the bob, the pendulum oscillate. Do you think the spring balance reading will remain the same, or will it change?
No, sir.
No.
So will that allow me to measure tension?
No.
No.
It will allow us to measure tension, I think. Yes.
So it will have a reading. Is that reading tension?
Yes. The reading will measure the extension in the spring, right? The reading would, and there will be so when in general theta, its orientation at some general theta, it will calculate the tension, the extension at the function of theta at different.
It will calculate t cos theta. It will give us t cos theta, I think.
Yes, it will calculate t cos theta. No, not t cos theta. It will calculate t, I think.
Okay, we'll make some assumptions.
So the extension, the force on the spring will be basically due to the tension. So at every point, the tension will basically give rise to the extension of the spring, and so the more the spring extends or contracts will give just the measure of the tension at each and every point.
So my question to you is, can you plot? So you know how the bob is going to behave, huh? Small oscillations. This is absolutely well known to you. So you'll have the bob in the center and it is kind of, go oscillating like this, like a pendulum, right? That's how it is going. And you can actually plot theta as a function of t. The typical sinusoidal behavior. Okay. Can you plot tension as a function of time? Okay, that's my homework to you. Go back and think of what, or you can actually calculate, right? And does it make sense? Does it make sense that how should tension vary as a function of time? Okay, I think I will move on. You can go on discussing. Many of these problems. Okay. We can make it much more complicated. We are speaking of constraints. We can make much more the constraints, or the concept of constraints, much more complicated. We can make the constraints explicitly a function of time. Okay. Now, if the constraints are explicitly a function of time, if that equation f is a function of Ri as well as t, or it can be independent as a function of t, okay, as in the previous examples. So if it is a function of explicitly a function of time, it is called a Riemann constraints. And if it is independent of if the equation is independent of time, or explicitly time doesn't appear in the equation, it is called scleronomous. So can anybody give me an example of a constraint which is explicitly a function of time?
So the motion of a gas in an inflating balloon.
Okay, the motion of a gas in an inflating balloon, that yes. So the position of the walls are an explicit function of time. That's what you're trying to say.
So what about the spring pendulum you were talking about?
The spring pendulum, yes. So does that have a Riemann? Is it a function of time? So what about, okay, so let's
the length is changing at each and every point.
Yes.
With intervals of time. So the length's always changing. So there's no we can't write sum f equals to 0 because it's always changing.
Okay, so let's assume that this is my bob. Hopefully you people can see it. Okay, and this is my point of, what's happening? Just 1 second. Yeah. Okay, so that's my bob. And that's my point of support A. Okay, point of support A, and my equation and my equation basically is these are my coordinates. Okay, and the position of A, let's say I give you by another set of coordinates which are called x1, y1. So the rigid slash massless string essentially gives me my first equation of constraint, which tells me that x1 minus x whole square plus y1 minus y whole square is equal to L square. That's my first equation of constraint. And then I say that the point A is not static, but the point A is moving according to the equation f of t, let's say. Okay, f of t. So this is y. So I'll modify it a bit. I'll just write it that is y. Okay, and this is probably how I can algebraically state exactly what was suggested to me. Right, and if that, let's say for example, this motion is also an oscillatory motion. Okay, so this point can actually go on oscillating about its amplitude with a certain amplitude A naught. Okay, and at the same time the particle, actually the bob, is allowed to oscillate in the vertical plane Okay, so you have a coupled oscillators. Okay, but as far as this particle is concerned, the constraint on this particle is explicitly a function of time via the movement of the support, and therefore this kind of constraint essentially becomes a Riemann constraint on the system. Okay, so you see these are the various things which actually comes into picture. Okay, so we have learned about constraints. We have also tried to appreciate that there are not only constraints, but the physical reality is that each constraint comes with an associated force, which is the force of constraint, the constraint force. And these forces are measurable. They are physical quantities that, the moment you, yes, Praveen Murali says that, yeah, double pendulum is another example. Yes, a double pendulum is another example. But it is only with respect to the second pendulum that that is the case. If you take the double pendulum in its entirety, it has a fixed support mostly. Okay, so do keep that in mind. Okay, so what we learned about constraints on the system, that there is something called constraint, and they have an algebraic form. And that is very important, that we learn how to express it in a mathematical form. Associated with the constraint is constraint force. And these are physically measurable quantities. So these are not Gedanken artificial pseudo force like things, but these are physically measurable quantities which appear on the system. Okay. Okay. And then yeah. So if you keep these things in mind, then let's look at the following. So let's look at a particle which is free to move. Sorry, just give me a second. Let's look at a particle which was free to move in 3 dimensions. A particle free to move in 3 dimensions, it has three degrees of freedom. It has 3 degrees of freedom. Okay, so if there are n number of particles, then if there are n number of particles, then you will actually have 3n degrees of freedom. Okay, so let's say you have a ball. It has 3 degrees of freedom. Let's say you have a dumbbell where this rod connecting the dumbbell is a rigid massless rod. Okay, so how many degrees of freedom does that system have? If I assume that the 2 particles were independent, then each particle would have 3 degrees of freedom. Then you would have 2 into 3, 6 degrees of freedom for this system. And then there was one equation of constraint, because the distance between these 2 particles was a constant. So I would subtract 1 from it, and this would end up having 5 degrees of freedom. So if I have 3 particles, let's say 3 particles connected by 3 constraints, equations of constraints, then it's a triangle. Okay, it's a triangle. And can you tell me what is the total number of degrees of freedom of this system?
So 6.
How?
So 3 constraints, 3 particles having.
So are these 3 constraints independent of each other?
No, sir.
They are not. So I can't. These 3 equations of constraint, are they all independent of each other, or they are not?
So they are dependent on each other, I think, because they are.
Yeah. Instead of jumping into answers, you should spend some time and think. Okay. In short, I am going to a rigid body. Okay. So a rigid body is made up of a very large number of point particles, isn't it? Okay. So there are
Sir, they are
large
dependent.
n number of point particles, and for every pair of point particles Rij, I can actually define a constraint, right? So my question is that that how many degrees of freedom does a rigid body actually have?
6.
Okay, so yeah, how do you prove it?
Sir, because the Rij constraints equation are not independent with each other. Let's say we have one.
So initially there was 3n.
Yes, there are 3, and let's just choose one. Let's just focus on point 1, then on 1 point, and we choose a second point.
Okay.
Then distance between them will be constant. Then all other points can can be related with the first two equations.
How do you say that? That's exactly the question I'm asking you. How do you say?
So when we fix one part,
Yeah, go on.
So I meant to say we do not need, for example, if we have 3 particles, all the 3 are bound in a triangle.
Yes.
I mean, they are having this relation. So we don't need more number of, relation, because that will make it redundant. These 3 will be sufficient.
See, I'm in a science class. We don't need more number. We will make it redundant. Can you quantify? You should be able to, when you're giving an answer. My request is that you should be able to quantify. This is a science class. More, less, these are all relative terms. So that's not the point. The point is that can you actually quantify and actually tell me that, okay, that is very clear that there are 3 particles, and it is very clear that there are 3 rigid rods. Okay, there is no denying these facts.
so when we fix one particle, so when we fix one particle, it can move in a sphere of any radius or any theta and phi. But when we fix another particle to it, so it can only move in a circle.
Yes.
And for the third particle is always constant. So basically 3 plus 3 coordinates are required.
Okay.
So 3 for the first one, 2 for the second one, and 1 for the last one.
Yes, you're right actually. Okay, that is a far better way of expressing things than in the reductionist form that I was taking. Okay, so in general, so if that is clear to people, in general, if there are n number of particles in the system, there will be 3n degrees of freedom, and if there are k equations of constraint, then the total number of degrees of freedom in the system will essentially be equal to 3n minus k. Now, as he said, that you'll have to figure out how many k equations are actually there. Just because I can write so many for every NC2 number of equations doesn't mean that I actually require all that NC2 number of equations. If you know what I was referring to combinatorics. Okay, so so that's what we more or less get. I think I'll just stop here. And we'll continue in the next class, which is next week. And by weekend, I will share my lecture notes with you. I just wanted to also show you that. Maybe I'll do it later. I just wanted to show you my lecture notes, what I'm trying to do. But we'll do it later, and I will also come up with the assignments which will help you, probably clarify your doubts. Okay, that's all for today. I think if you have any questions, you can ask me. But otherwise, I'll just end it here.
Sir?
Yeah, go ahead.
Sir, when we define that the degrees of freedom is equal to 3n minus k, so the factor of 3 is only coming because we are considering a 3-dimensional space, right?
That's right. So if we 2-dimensional space, then it will be 2n.
Okay.
Yeah. So it's a 3D space. Yes. So, for example, in that simple pendulum problem, I don't know if you have heard of something called a conical pendulum. Okay. If you look at the motion of a conical pendulum, it actually takes place in 3D, and you would actually require 3 degrees of freedom to describe the motion of the particle. In the simple pendulum case, it's a plane motion which we actually analyze. And that's why mostly we get away with the plane polar coordinates or XY coordinate. Okay. Right. So I would also ask you to, therefore, those of you who are interested, go and solve the conical pendulum problem. Okay, the constraint is exactly the same. The constraint is exactly the same. It's just that the difference is that, you know, when you have that plane pendulum, the bob is actually hanging, and you give it a force. How you start it off is you just giving it an impulse at its equilibrium position, or you drag it to one end, one of its extremal positions, and let it go, and so that, you know, it goes on executing the simple harmonic motion. In a conical pendulum problem, it's a bit different. You actually you have the bob hanging out, and you take it to you kind of make a small angle, and then give a push, not along the plane that you made the small angle, but perpendicular to it. Okay, perpendicular to it, such that the pendulum actually moves in a circle, and the string describes the surface of a cone centered at the vertex matching the point of suspension. Okay, so if you for example, you know, try to solve that problem, you will see that the constraint is again the same, that the distance of the bob from its point of suspension is a constant. But the degrees of freedom that you will actually require will be 3 minus 1 rather than 2 minus 1. Yeah. Okay, is there any other questions? So if you don't have any other questions, then I will sign off today, and I'll pick up with you at some stage during the week. Thank you, everyone.